Change to called.
Everyone.
Sorry, I know that command doesn't.
What did you call?
No, you can't pull.
Get that.
I'm loading.
Okay, class started. So collaborate. Okay, let's fix that later.
Wait, I'm right there.
Okay. Hey guys, this is I add today simply because we run into some issues. So I would say our team is not very big, just 9,
10. 10.
This is why you kicked us. There should only be 8 people. Why are there?
Okay. So even we have 10 people, we run into a lot of like version confliction issues, right? Even though you work on a project, you have a lot of conflicts, right? Co-conflicts, right? You have some push and pull confusion, right? When you work on your project, you will get more used to it and how to deal with it. Because can anybody tell me what's the correct order to commit a code? First, you need to do a code change, right? Then do what? Commit. Then what?
Pull.
Yeah, git pull. Then, yeah. Remember, okay, always 4 step. Do coding, commit your code, git pull, git push.
What's the purpose of git pull in that?
Git pull is get the remote change from a teammate to your
And then you file the welcome push again.
all right?
So yeah, everyone has a
So if you pull, it doesn't undo your code changes.
It will merge. If you guys do in the same line, you will merge. So actually the best practice is like this. Every day before you do any coding, okay? So you should do git commit to whatever stuff you're doing, right? Then you did a git pull. So in this way, you pull your teammates' change before you work on something new, right? That makes sense? Otherwise, you work the whole day. So sorry, I changed the code yesterday. You just redo my work today. Hopefully, you guys answer, right? So actually, the best practice it is to keep saying that git commit, git pull, okay? Pull all your teammates, then you start coding, right? When you start coding, you do another git commit, then git pull, git push, right? Basically, the order is always git pull or push, or you just git commit, git pull, git push, or just say git commit, git pull if you don't want to push. The last step can be skipped. That means when you are starting your project, new project every day in the morning, you should say git commit and git pull. Got it? Get latest code. Okay, that's one thing you have to keep in mind.
Branch, right?
Yeah. So sometimes they share one branch. Yeah. Okay. The other thing is happened today. It is we need to have some kinds of version control rules. Even though Git provide most of the change, like the blessing on you guys, right? But you still need to follow some rule to avoid trouble because program is still programs, right? If you don't do something right, you still have loopholes. Okay. First important rule it is never release from master branch directory. The correct way it is branch off from the release candidate. The release candidate, it is any branch. Okay, if it is from master branch, you branch from master branch. If it's your personal branch, you branch off from your personal branch, right? So basically, you need to branch off from the release candidate, test it. You have to test it. After you branch out, you still need to test it, even though you already tested it before you branch. Okay, test it, fix whatever the issue you think you should fix, then tag it with a version 1 point something, whatever the version. Okay, then release it. Got it?
What do you mean by tag it?
How do you release it?
Release means you compile your code and deliver to your cell phone. Or if it is a CNC project, you tag it, release it. That means you save your project into step file, upload to the Google Drive and share with a friend and generate G code and right? Got it?
What do you mean by tag it? Like just name the branch something?
Give a version name.
Wait, so every
1.0,
time
1.2.
So you mean when you commit?
every time we run it on the phone, we have to make a new branch. So
If you think that's important, you want to keep it. If you think, yeah,
That
if you want to keep it, if you think that's a good candidate, you should keep it. Especially the branch before you achieve something important. For example, we have a milestone. Say Robert should do navigation. They should finish autonomous. Should finish all telework. And whatever the milestone, you need to tag it. Because that's supposed, if basically whatever you think, that's a good version ready for competition. Or it meets a milestone, tag it.
You mean in commit message?
Yeah, and tag it. Give a name. Okay?
So what do we name the branch?
What?
Message.
It's not a, there's a command called git tag. It's a git tag command. Okay? So let me tell you later, okay? But basically you need to remember, you need to follow this order, okay? And the second very important rule, it is never merge changes from other branches to those release branch. Say for example, you release version 1.0. You find out there's a bug in 1.0 and you have a fix in a master branch, then don't merge from master branch to the release 1.0, okay? Because you ruin it. Because the reason we want to tag it is we have a snapshot of your code or your design, so that we can go back to it later. If you merge from somewhere else, when someone 2 months later you want to go back to a branch, it doesn't exist anymore. You cannot go back to a good version, right? So that means whenever you release, never touch it. But if you do want to derive on top of the release branch, make a branch out of it, okay? Then do modify code change, but never change the branch. Got it? Okay. So basically the release branch should be frozen and read only. Got it? Okay. The third very important rule is no last minute changes before release. Like today, we say we want to make CNC cut at 1 p.m. No more change, okay? The frozen is frozen, cut is cut. And either release as is with no bugs or no release. If you find the bug is severe, not worthy to do it, don't release it. Keep working on it. If you think you can live with the known bug, just release it and find a way to avoid the bug. Okay? Because the thing is, known bugs are easy to handle. Then surprising bug, right? If you know, it's always fail like this way. For example, you always, before the competition, you always find out your button A never work. Then you just don't press button A, right? Right? Got it? All right. The third rule it is version number should start with 1.0. Minor changes should increase the minor number. For example, 1.1, 1.2, 1.3, right? If you have big changes, should increase the major number, such as 2.0. For example, if you totally change your chassis to be like a completed seal, like with a back plate, that's considered significant change. That's a 2.0. That's 2.0. Right? That's 2.0. That means the correct practice today is we should branch of whatever the last night spilled, with tag is version 1 and fix it and copy it out. And whatever the new change you want to do with the back plate, with the seal the whole chassis, it should be going to 2.0. Right? Got it? Okay. So, and you have a mini changes, you can even increase more, like a 2.0.1. Okay? Got it? Okay. So that's a consequence. If you violate those rules, will make your robot not stable and lost track of good versions. Like it happened to us. We lost track of good versions. That good version we test for 2 weeks. We carve out the cardboard and make sure it works. That version is gone.
Yeah.
Right?
They destroyed it.
Can you still find it or is it just gone?
What's
No, I have it, it's correct, I have the right.
It's correct,
version.
okay. Basically, it's still unknown, right? Are you sure?
I'm sure,
Oh my
it's
gosh,
correct.
So the one I found in.
But why do you have a
If we
corner?
add
Well,
updates
the
to it,
model doesn't have a corner, I don't know.
well, after we finish cutting that and we update it, then we have to remember to branch it out next time, like 100%.
Okay, so the other consequence is probably minor, but it's still, so your robot will always have something strange things going on. You don't know why, because always there's a little bit thing here and there. It's a last minute change, unpredictable, right? More like 99% of the time work, 1% doesn't work. That's exactly happened to us in the World Championship last season. 90% of the time they work, 10% doesn't work.
Always has something
And
strange.
So this is most toxic situation because we don't know how to fix it because it's hard to reproduce it. When you try to fix it, it's honestly it always work, but because you say, whoops, it doesn't work. So right, that's really hard to fix, right? So that's why if you don't obey this rule, it will happen very often. It's really hard to fix. And the other one is your project will miss the deadline. It's like today. Today's deadline is 1 p.m. We need to cut. Oops, we slipped the deadline. We cannot do anything, right? And this is also a pitfall why strong team doesn't perform well in the competition because they think they're too smart to be smart. What does that mean?
I don't think I'm smart enough to understand that.
Yeah. So basically,
Hold on.
your overconfidence. You think you are smart enough to skip a task to fix something or to reach a goal,
Well, that's not smart.
right? And as a result, it doesn't look smart because your stuff fails, right? So that means well, my definition it is too smart to be smart,
So just dumb.
Yes.
right? You are actually the team is a strong team. They can fix the problem quickly. They can design things, really cool things, but nothing works because
Theory and practice are combined.
you lack of time, right? They just hopped in too much. You hop too often, you will fail, right?
Yeah, it is. It'll always be there.
Okay. So, and for personally, if you keep doing this in your team, you will find out you hurt your team more than helping your team, right? Right. So, people will might label you reckless. Okay. Be prudent. Okay. So, especially when we have more robot parts put together. Okay. So, okay. Let's go back to today's class. So, today's class is about sensor. Okay. So, how many of you finished the
Dancing robot.
dancing robot? How many?
Everyone except for
Okay. So for the rest of the team, the other teammates should help them. Dancing robot is supposed to be really easy. Okay.
actually, I literally just
I think means version is supposed to work, but mean probably too smart to be smart.
Actually, I had a bunch of Java key problems in the beginning, remember?
Why is it that whenever I run, it's
So,
never giving me any?
Do I tell you in the beginning?
Yes.
Start from the seventh branch or from the seventh branch.
I
Everything
did.
is okay. You say no. You want to branch off from your own branch.
No, I did branch out from the summer branch. And
Okay.
I still had a heap problem.
Okay.
It's like,
Okay, that means your branch is somewhere is not clear. Okay.
no, it means
Okay. It's over. A second thing it is, if you follow the example code in accesses, because I gave you example code in accesses, right? You start as a starting point, then work on it. Don't put the last season code. You just put the last season code. You think you can get a shortcut, but actually you got a long
Hold
cut.
up.
No.
Oh, God.
it was working until there was some iron.
Yeah, because you want to make a robot dance work because robot dancing is a very simple code, right?
It is like I have it uploaded.
Yeah, everything just based on a timestamp. When the timestamp reaches, you do something. That's so that simple, right? The problem doesn't work in the main branch. It is mean incorporate lots of code from last season. It's do something extra. It's not just for robot dance. It has what? Has the euphoria finding with all the
Oh my
Sorry.
God.
why are you doing that?
Oh my God.
So this is why say especially when you do programming, okay, if you ask you to do okay, this is a starting point, okay, just use that starting point, do it, Alright? So if you try to hop, God knows what happened when you landed. Alright? It's better to walk step by step.
To
Okay?
be fair, you never
So-
said.
Mine was
I'm
Jackson.
the type of person that trips up.
I know, right? Balls and holes. Relatable much.
Okay.
I trip without the holes.
Okay. So the rest of the team, okay, should help whatever the team doesn't finish, including the Derek. Derek because on vacation, so we all of us will help you catch up. Right? Don't feel bad. Right? The first couple of homework actually is really simple. It's help you to get used to how the FTC robot controllers put together, how do you assemble it, and what's the fundamental programming concept. Okay? I gave you 90% of code. You just need to figure out 10%. Right? Is that right? Okay. Okay. Now from this today class is for sensor programming. Okay. From today's class, I won't give you any code because whatever the code scaffold, you can get it from last access, last homework. Okay. And from this lesson, I will grade your homework. You will actually get points. Even people based on how you write a program, I will grade you.
Wait,
Right?
so none of
And if
these
you-
are worth points?
Right now you didn't because you just so in order to get you to do the quiz, you guys just hand in something blank or something. Coach, I will hand in later. So it's get passed, right? Did you do that?
No.
Hold up.
So we did all the.
Wait a
You
second.
did it before the quiz, right?
No. Or something, I don't know.
Yeah, no.
I did.
I didn't put in a bunch of random stuff.
Most of our responses were.
When you told me to do it, I wasn't there, so I actually put in the text file.
Okay, cool. So anyway, from now on,
Copy.
all your homework will be graded. Okay? So, okay.
So this lesson.
Wait, is it
so the
for- is it
previous
for-
lesson's homework isn't graded.
Is it on
Wait,
the curve?
is it also counted on like writing neatness? Like if you
Yeah.
indented correctly?
Yeah, you want to make it.
Like
No, but if you copy and paste it.
Legibility?
Yeah, like
If it doesn't have
No, if you
legibility.
copy and paste it, and that's like, it messes up everything.
I will focus on more function. How you implement it. It's a
It
common.
doesn't function without proper indents.
Yes, it does.
It's Java. It's
For
functional.
me, it doesn't.
Bro.
No.
Coding in Python?
No, I'm not. I know it doesn't Python, but it's not brackets.
No, parentheses are
Maybe
saying.
it's because they
No,
use
in
different
Python without
compiler
brackets,
most
they
of the
use
time.
Oh yeah.
And the other thing is, I recommend you take a video of how your robot works and post in the Apollo YouTube channel.
YouTube channel.
Social media.
Wait, we're on the YouTube
Yeah,
channel.
because-
Derek went to the thing, our video, the servo is on there.
Yeah, because
That's not the YouTube channel, that's the
YouTube channel. Because I need to.
It was a YouTube video.
website. I mean, look.
I need to count on the YouTube video to give you credit because it show me how your robot works, right? Right. At the same time, there's a side effect. It is you guys can use that video to do social networks.
It's still.
You guys can use the video to do the networking, right?
So you want me to film it with my computer?
Either way. So just take the video, okay? So.
I can't find garbage.
Okay, let's go back to today's class. Okay, today's class is really intensive. So if you don't understand, you have to copy and paste the code and try it out in your robot. Okay, so let's talk about what's the common programming pattern for sensor state machines. Okay, so all of you know that inside the loop function, you can implement state machine, right? You can implement multiple state machine. Do you guys know that? You can put a multiple switch statement there. Got it? So right now, this is one of the state machine. Okay. In this first lessons, we only have one state machine or two state machine, right? In the future, we have an embedded state machine. Do you know what is embedded state machine?
Stay in the state.
That means in one of the state here, it's running a state machine somewhere else. It's called embedded state machine.
Oh, it's like what we
Like
did.
a nested state.
Yeah, nested state machine, right? Got it?
It's like what we did last time.
Yeah. Okay, but for the sensor, how you program the sensor? This is a basic component. In one of the state, you need to read the sensor value. Okay, you need to first read the sensor value. Then, based on the sensor value, you do some calculations and make decisions based on business logic, right? Then you send command to I call actuators. Actuators are motors, whatever you change the word, as an actuator, including the speaker, light, anything is actuator. Okay. Then you make a decision whether you need to change the state, right? Right. And what states change to? You don't need to say always stay state 1, go to state 2, 2, state 2, go to state 3. You can jump to any state. Got it? And if you really need to change the state, you need to clean up the current, whatever the current state. In the dance program, what do you need to clean up? You need to reset the timestamp, right? So that you remember when is the last timestamp, right? Right? You also might send some command to make sure the state end properly. For example, you want a robot to stop, then you should send a motor command and set power 0, right? So basically, you have to follow these 7 steps to implement one state in the state machine. Okay. Then after that, you can have a lot of states. State 1, state 2. And you can use any number as a state. For example, here you can have states 9 million something, totally fine. Okay. Also, you can jump to any state.
I wouldn't be able to
Right?
keep track of that.
So if you jump to this state, it's okay to jump back from a loop. Right? This is a loop. In your dance program, when your robot reach the last state, you loop back to 0, right? So you can repeat things again, right? So this is how you introduce a loop. Got it? Got it? So basically, the robot looks smart because this is how you just use the state machine. So the robot state hop from state to state. So like it looks like smart. That's not intelligence, right? Because whatever is making intelligence is because you do the program here and make a decision at each step. Okay? If you handcraft this properly, you will make a robot really smart. For example, you can say in the sensor detection, if you find out you are blocked by something, you can jump to a state. Say, make a right turn. Right? If you find out in front of you there's no obstacle anymore, you say, I'll make a left turn back to the track. Right? Got it? So actually, this is going to be in your homework. The homework of this lesson is a little bit challenging. I will give you a little bit longer time to finish. All right? All right. So let's go to the next one. I call iterative optimal. Most of the time, so in a couple of in last few lessons, we focus on the iterative optimal. You can see you have an init function. You have an init loop function. Helena, what is init loop?
Or what?
What is init loop?
Yeah.
What do you implement in init loop?
What happens once you click on it?
Yes. If you have a long init process and you want to check the progress, for example, if you init a robot arm to a 0 positions, then you should put your code here, right? Keep checking, right? Basically, this is an event loop. Okay? And the other thing we can put here is like in last season, we put object detection code in the init loop, such that when we hang the robot on the lander, we can see whether we find it or not. Got it? Okay. And when you press the start button, you will run start code, right? When you and on in here you run loop code, right? This is called iterative mode. Okay. And all the program here has to be really fast. If you're in the loop function, if your function takes like a couple seconds to finish, the robot will think it's dead. You will reboot it. Got it?
So sometimes when I'm driving, I feel like it takes more than 1 second to react to when I press the button. So does that mean?
It means there's something slow in the loop function.
Okay.
When you, for example, you unnecessarily query the motor encoder position multiple times. Why you want to do that? Right? So for a good programmer, you always read the sensor once and remember the state, just make a decision. Don't say, oh, keep pulling. That's slow. Right? So we can help you to do code review to make things fast. Okay? In the last year, we just dump code there. No, I don't care, you don't care, and probably you guys don't care. I definitely care, but I'm a coach. I'm not supposed to do everything for you, right? So this year you guys will care. Right? You ready? Right? Cool. Okay. Okay. In today's class, we will introduce another mode called linear mode. Linear mode is trying to solve the problem. It is in the iterative mode. You say it's a little lagging, right? The linear mode, it is you basically write everything in a while loop. You don't do event loop. You just put everything in a while loop, right? So you have really tight feedback. Then you just count on event loop to do this pulling. So the robot will respond faster, right? But you pay the price it is making you really hard to do complex programming. Because you only have a one while loop. You have to implement everything in a while loop. It's hard to put a couple of sensors there. Your code will be really messy. Yeah, right? But you guys should know, because if you find out in Talio you want your robot to be really high performance, then we should go to this mode. Okay? We hand grab it carefully and make sure it doesn't mess things up. Okay? And basically, in the run mode, what you need to do is you just extend from linear mode instead of extends from up mode. Okay? Then you get this linear mode. And there's only one function in the linear mode, is run up mode. And basically, you need to implement everything in this function, including how you init all the devices.
How run through once, or is it
run through once? Once. Okay. And you have to wait for start here. Okay. Basically, this is a start init loop function. Right? You have no way to implement init loop now. Okay. So, and then you basically put whatever in your loop function inside a while, because while up mode alive, you keep doing this thing. Okay. Because this input everything in the type loop, so it's looping much faster than the loop function in the event loop. So you'll have higher performance. Question?
In normal off mode, can you like skip one of the and it would start loop or stop if you don't have anything in there?
Of course. You can skip it.
Okay.
Right?
So you don't even need like write anything. You just,
No, you don't need to run everything. You can. It's okay to be empty. So basically, this function is same as this function, right? Star here, init loop. See that? Everything here in the while loop is at here. Oh no, sorry.
Is this slower?
This is a type of sheet. I will change it. It's not init loop. It's a loop. Okay. So, okay. Basically, it's your personal preference to choose op mode or linear mode. It's iterative op mode or linear op mode. Okay. So it depends on how we want to use it. But the rule of thumb is code with linear mode is faster and simple, but less flexible. Right? Code with op mode, iterative op mode is cleaner and can scale up to be very complex operations. So basically, it is autonomous mode. We'll try to use iterative op mode as much as can. But for Talio, we should use linear mode as much as we can. right?
Quite about 20 civils.
Right? So, okay, let's go back to the first sensor, which is touch sensor. Touch sensor basically it looks like this, right? It's somewhere here. You can find it. Okay. So there's a white button here. If this same button is clicked, then the program does. Actually, there are a lot of notice. Oh yeah, that one is touch sensor as well. There are a lot of touch sensor there already. Basically, in your gamepad, button A is a touch sensor, right?
Oh, okay.
Button B is touch sensor,
Oh,
right? So
Do we actually use these on the robot?
yeah, in a couple seasons ago, we use this to detect the what initialized arm.
oh.
The arm mode will keep turning until this button it is got activated. Then you memorize as a 0 position.
That's
What if we use this so that whenever so it prevented the arm from reaching the ground, so let it smash to the ground.
Oh yeah, you can do that. Yeah.
What if like
If
dig
you
into the
wanted
ground?
to.
I mean,
Like, so when it hits the ground, it's like.
no, so when it touches the touch sensor, it just
Okay.
stop moving down.
Yeah, in this. Okay. So that require in that case. That requires some like a 3D printing object going because this button is too small,
Yeah.
right? It's hard to say always touch the screen, right? So what you need to do it is you have to put this in a long
Close to the
level or something like that. So when this long level or there's a whole bumper is pressed, this thing will be pressed. Okay? Yeah, basically in this lesson, the first homework it is write a program and put the touch sensor in front of the robot. Press button B, the robot will move forward. And when this touch sensor is activated, when it bumps to something, the robot should stop and reverse. And stop.
Reverse automatically.
Reverse by some steps and stop. Basically,
So we just stick it in the front of the robot,
Yeah.
drive it into a wall.
you have to talk to the wall, and you should stop it. Otherwise, you crash into a wall,
So
right?
the power to one.
Oh my god.
So what the robot in the first lesson, first homework today, it is write a program, put the touch sensor on the front, and press button A, robot move forward. If the robot touch something, you should stop, then back up by some steps. Stay away, right? Then stop. Right? There's a couple of state machines, right? Right. To use the touch sensor is very easy. First, you need to declare touch sensor, and in the init, you need to go to the hardware map. It's called hardware map dot touch sensor to get the touch sensor name, whatever the name you put in the cell phone controller configure, right?
Oh yeah.
So in that case, you can put a multiple touch sensor there because the name they have a different name. You can have a touch sensor 1, touch sensor 2, touch sensor 3, right? And actually, the second homework of today's homework it is use touch sensor to make the robot can do navigation through obstacles, right? You can put the touch sensor on the left, touch sensor in the center, another touch sensor on the right. When the robot hit on the front, when the touch sensor activated on the front, robot should back up and randomly turn, either turn right, it depends, right? Right? And if the left sensor is got activated, that means you should turn right, right? If the right touch sensor is activated, that means you should turn left, right? If you build up this state machine, the robot basically can just keep it bumping here and there, but eventually you'll find a path out.
So do we make it straight or do we make it turn?
Make a turn, you can, it depends on how you want. You want it to always turn 45 degrees or always turn 30 degrees. Okay?
If you make it turn, then the two.
Yeah, it'll turn. It'll be the front sensor again.
What?
If you turn it, it's gonna be the front sensor when it hits something.
No, it's like this, hey guys. Think about it. Say, suppose this is a robot. If your left sensor is activated, right?
Can we just make it straight?
Either way, right? Usually people will put the left sensor on a 45-degree angle. That means you partial of the robot is hit. Robot like this, right? Partial of the robot hit something. Alright? So that means what you need to do is you first need to back up a little bit and make a turn and go straight and turn back, whatever, right? Right? So if you want to use this program to do like a maze runner, it's going to be fun, right? Then you can try little by little, right? Or you can turn 45 degrees, depends on you now, right? How smart the program is on your program now, right? So you can turn, you can every time you try a little bit angle, try again, but it's slow, right? Or you can try much bigger range and see whatever it works, right? So there's a lot of things you can work on now, right? So basically, it's a second homework. Question?
Is it like the maze runner thingy we did with like the small flat robots from like 2016?
Yes. Exactly.
Wait, the white ones? The dome ones?
Yeah, this one.
No.
Wait, I remember that.
I feel like I remember, yeah.
Wouldn't it be better to use like a distance sensor so you can sense like the distance between like all
Before you
like
run
the
into it
3
on one?
directions and check if one direction is like farther from one another so you can turn?
Yeah, exactly. That's homework 3. It's
Oh
already
my
there.
God. Well, you know how to do it too.
Wait, what?
Internal.
I watched that. Like those competitions where they have like one little car and the car searches every single position and it speed runs the whole thing.
I watched like 30 minutes.
Yeah.
That's actually cool.
Yeah.
Is that how Japanese?
If some of you, like me, is lucky taking my class to do this, to do a maze runner, he know most of it. He knows some tricks already, right? But hopefully you still remember.
Hopefully it doesn't remember.
Okay.
No, because they haven't done the dance.
Okay. So at here, you guys.
It keeps on running the run.
What?
We could do it using Python.
Say some?
Running is in Python.
No.
What?
Hold up.
Okay. Let's stay on class. Okay. So at here, you know how to create multiple touch sensors now, right? And to use it is straightforward. Just say what a touch sensor is pressed to do something else, do something else. Right?
That's
It's straightforward, right? Nothing complex, right? Got it? Okay. So the next sensor is called compass sensor. Okay. Compass sensor is usually to be really popular in FTC game in the early days because they don't have a gyroscope. Or at the moment, gyroscope is really expensive, right? So because the total count on the compass sensor to know where the rover heads, right? But at here right now since we have a good gyro, we're not count on it anymore. But it's still useful. What if the gyro got confused? You should use this to double check the things it is in right
Does my
track.
phone have a built-in one?
Yes.
Mm.
Yeah. Also the Ralph expansion hub has it. Okay. This is very useful when the gyroscope lost track or drifting too much. You can basically use compass sensor to calibrate the gyro. Got it? Okay. To use it is very straightforward. First you need to declare private compass sensor equal to null, then get the address from the hardware map, right? Then you should give a name to it, right? Then init loop. Sometimes this is one example of init loop. For the compass sensor, you need to do calibration before you use it. So this is why we do it in init loop. Okay. So that means if you implement this correctly, the start button won't show until the campus is calibrated. Question?
It says if parentheses compass sensor calibration failed. Does it mean like succeeded? Because it says if you do that, then it says it's ready to start.
Oh yeah, yeah.
It's the thing.
Yeah.
In front of it.
If not fail, and here's a if.
Exclamation mark, that means not.
Oh, okay.
If not fail, then you say ready to start.
Alright. I see.
Alright.
Is there no function to say if it worked?
It's up to you. But the API the FTC guys gave us is like nothing. Okay.
Wait, the gyroscope sensor looks exactly like the touch sensor.
So
Just take
this
the gyroscope sensor and just break it.
Like, wow. Like, it's literally the same.
Okay. So
Does it have a button? That picture doesn't have a button.
we are not using this. This is a robot, modern robotic sensor. We're not using it anymore. We use gyro sensor inside the IEV card. Right? Okay. To use the compass sensor, you just say get direction. You give you direction. And what the direction means? If the north, if it return a double. If the return value is 0, that means it's north. If the east is 90 degrees. So basically from 0 to 360, right? Based on this, you know which direction it points, right?
Why is it in dome then?
Right? Okay. So gyroscope is quite similar. Okay. You use it. You declare it, get address from here. Init loop is the same thing. If gyroscope it is calibration, then you should not go to the start state. Got it? Yeah. Right. To get a direction, you just say get heading. Oh, this gyro sensor has a utility function. You can reset the heading. So in the beginning, if you run this command called reset z-axis integral, you will set the current heading to 0. So it's very useful for autonomous, right? When you press start, it's memorized whatever the starting position is 0, right? After that, right? So you know what's the orientation of the field now. Got it? And to get where's your robot, it is the same thing. Get heading, return 0 to 360. If you are looking on the front, it's 0, right? If turn 90 degrees is 90, right? If you turn backwards, it's 180, right? So, okay. For the IMU actually has integrated a lot of sensor there, but most of them we use as a driver. Okay? IMU means in inertial measurement unit. Basically, there's a small little sound bar, sound fork,
Tuning fork?
sonic fork, tiny one, okay, inside the IUV, right? Basically, when your robot moves, you will cause vibration in the.
Is it a tuning fork?
Huh?
It's like those like things that you hit against a table.
Yeah. Question?
So for the gyro sensor, you can do in X, Y, and Z axes, right?
For that one, only do in Z.
Only Z.
Yeah, but it also do X and Y, but you need to do your own integration.
Okay.
It did Z for you. Because most of the gyro, we just need to know you turn left and right, right? Right? All right. So, and at here, it's basically use a different mechanism to do a turn because it's a small little forks inside the extension hub. When you turn, the fork will deform, right? When it deforms, you will generate small current. Based on this current nodes, you turn left or turn right, or you make acceleration in X, or you make an acceleration on Y. So based on that, you do integration and figure out what it is, right? Okay. So, and to use that, you basically say so it has a really strange name. So BM005MU equal to something. Sorry, that's the API FTC gives you. Right? Okay. And you need to set up the parameters because it gave us more advanced feature. This one, basically, you can change the like a degree angle. You can use arc or use a degree. Right? It depends on product. Radians or degree. All right. Or in acceleration unit, you can either use inch or use centimeter. It's up to you. All right. Okay. And another cool thing is you can save your calibration file somewhere such that make your initialization much faster. You don't need to calibrate. Always calibrate. Right? Okay. So then you can also change the different like integration algorithm to serve for different purpose. Okay. But this is a good one. We just stick to it. Okay. So then after that you get the address from the hardware MAC, like this. It's the same thing, right? Then you need to say call this init parameters to actually start to use it. A lot of time you say, oh, I got IMU error. Usually two things happen. Either you forgot to play video game, it means computer, or sorry.
What? Wait, hold on. You forgot to?
Either you forgot to call IMU initialize, or you call this IMU initialize twice somewhere. Right?
Maybe you call it twice
Maybe
as
we check that.
uninitialized.
No, you have got the IMU error. Because you already initialize again.
You said you got
And
it.
it's during when the IMU is activated.
I fixed the error.
Oh.
Yeah,
You activate it, it will fail. Right?
Coach, I still have no idea where it
Oh
called
my
twice.
god.
Okay, let's figure out later, okay? So,
I mean, it worked later, but like.
okay. And at here, there's one more thing. That's the thing we don't know last season. You know, and you guys are amazing by the gluten-free. The road is anyway, right?
Smooth boy.
Yeah, and you can always precisely stop somewhere, right? How do we do that?
I'm just,
IMU.start acceleration integration.
They are not using encoders today. They
No.
use IMU. Because if you call this magic function to start acceleration integration, you will the robot the IMU will start the integration and calculate your speed at each direction, x, y, z. And based on the time, you know where your robot moves and how much distance, right? Because if you know your speed and you know how long the speed moves, you absolutely know where you are,
Easy to.
right? So that means there's a function provided by the IMU. IMU not only is a driver, it can tell you the heading, right? It can tell you the position. IMU get a position.
What?
not
Oh
me.
my god. Wait, what is it returning though?
It returns the XYZ location when you press start. For example, in last season, we press start on the lander. Then that's your origin.
Origin.
Here,
Orange.
here.
Orange.
Orange.
That's your orange.
Here, we should call it for that. We
Okay?
don't know what it means.
That's your orange, right?
Yeah.
That's your orange. Basically, that's a 000 in XYZ. Okay?
Code apple tea.
Right? So then after that, if you call this position, you know where you are. You know you're in the crater. You know you are in a what's that? The depot. You know where you are. So this is why technically this is why a gluten-free they can do all the
New.
whipping things and go back to the lander and do all the precise dumping.
Yeah.
That's the magic. How come we don't know?
Well, now we know.
We're too smart to be smart.
All right.
Wait,
We
that
didn't bother
doesn't
to look
explain
it up.
dumping.
No,
The hub doesn't move when it's dumping.
it gets to the place where it needs to be to
Yeah,
do the dumping.
And then it repeats the
Got it?
which is cool.
All right. So we should use that. Another thing is a velocity. Okay.
Speed.
You know your speed of your robot. So for example, when you are travel really fast, and you bump into something, like last year, we travel really fast and bump to something, and we just keep moving.
We didn't use touch sensor.
We don't need to use touch sensor to know where I got blocked.
Oh, it's because you put power in, but you don't go. Oh,
Right?
yeah, okay, see.
Then we should stop right away. And then it's going to be your homework, okay? So basically, if you detect something, block it, you should go back and do something, or just depend on what, right?
The velocity changes.
Problem is how precise is this? So how?
We don't know. So
Can
we
go to-
in this homework,
Some-
let's experience it. Let's do some experience. We turn on it. Let's do measurements. How precisely the calculation it is.
This is like
Okay?
start with moving back. and
Because
forth.
basically, you can move your robot by like 2 feet, and look at the screen. How many feet is returned? If it's set 2 feet, that's amazing. Basically, the rule of thumb, you guys use this homework to learn this IMU to see how precise it is. And you guys need to figure out what's the resolution. For example, in a touch sensor, the resolution is whatever this movement, right?
Is there anything like that
Right.
that can determine
And
slight
for-
movement?
You can do a couple measurements. Say I move like a 10, I move 2 feet 10 times, and see what's the number it returns. Based on use the average, and you can calculate the standard deviation. Then you know how do we trust it. You can say, oh, this thing always missed by half an inch. That's pretty good, right? That means you can trust it. If it always missed like 2 inches, you know, oh, that thing is good enough to give us 2 inches resolution. That means in autonomous, whenever you need a 2-inch less than 2-inch resolution place, and you can trust it, right? But if you need to make really precise movement, you cannot use this. Got it? Got it? Okay. So the next one, it is also you can get angular activity, right? So in last year, because last year, what we need to do is, say, suppose you want to control how fast your arm moves to dump the mineral. If you use this function, you know the angular movements. You can make it constant speed, or to the speed, whatever speed you like.
So that would have worked in like auto mining.
Yeah. So basically, the reason the other team's robots look so great in autonomous, not because the driver is super good. It's because they write some.
It's not our fault.
Wait,
But also because
drivers can't control themselves.
Yeah, drivers can't control.
I mean,
Yeah.
we can like mess up the battery, but that's all we can do.
But you can let a robot control, right? So for example, you can just you push a button, right?
You mean
Ask
Yeah.
Tele or autonomous?
You can tile. You can put autonomous in tile,
Hold on.
See, it's not our fault.
right? So this is why I say I'm working so hard. I practice 600 hours.
Practice 2 times before we
Actually, I saw it. I saw I've seen a video of a team that had like automatic targeting system. So like their robot would automatically turn to the nearest target of scoring points.
Oh,
like,
we should have done
cargo
a
equipment.
function
It
that
was
just
really cool.
extended and done.
Okay. And the other thing is temperature. Guys, listen. Focus. The other thing is temperature. It's got temperature sensor on it. Technically, we can attach a temperature sensor on the motor. When the motor is overheated,
Oh my god.
Just let something like a gas stream.
when
That's
the,
like at least nobody
motor is
can
overheated, when the motor overheats, stop.
Like last time.
We should have like a
Like
fucking
gas
touch
sound.
sensor on our robot and have it play gas grid every time something touches it. So in competition, if a robot gets near us and like touches a robot, they'll
Oh yeah,
let it
it's
drive.
double major penalty.
We get all the
Okay,
touches.
put it backwards.
Then for some reason we're being oppressed by our own alliance
You
partners.
should just make it a hamster ball of just
Oh my god.
Or you can put it in a type of this fever
We
somewhere.
should just play.
If somebody got a fever, robot will say, hey, don't touch me, you're sick.
We should play. We should play like one
As
of
long as
touch the forehead to the IMU, like.
I'm told that everyone hates it, by the way.
Lame.
No,
Literally anything.
Okay, let's go back to business. The other one is the distance sensor. In FTC game, there's 2 types of distance sensor. One, it is through the light. The other one is through the ultrasonic feedback. Right? So
Yes.
even say, for example, on the other thing, it is even for the light, it's also has 2 types of sensor. One, it is count of the light intensity. Usually, the closer the object it is, the brighter the light is, right? Right. The other one is about flight by time. Basically, it sends out the pulse of the light and detect when the pulse.
Okay, you just expose yourself.
Okay, got it. So basically, ultrasonic sensor is a long-range sensor. It can detect about up to like a 5 meter to 10 meter distance. Okay, the light pulse sensor is a short distance sensor. Usually only detect less than 30 centimeters short range. Okay, so this is why the modern robotics is blending an ultrasonic sensor and flight
Will
light
bright
sensor.
light- Will bright light mess up like the distance sensor that is just like?
If they implement, if they calibrate correctly, they can back calculate it. It still give you good answers. Yeah? Because it's have to know that what's the back. Because it depends on the first. If you determine the distance by light brightness, you have an issue. But if you determine the distance by pulse, when you receive the pulse, it doesn't matter how bright it is. It just means if your object is black, that means you probably cannot see it because there's no bounce back signal. Okay? Right?
Yeah.
Right. So this is the shape of the distance sensor. And to use them, you can just follow the example here. Okay? You already, every sensor here, you have a how to declare it by the name like this, how to find it, how to use it. So basically, one of the homework it is, I want you guys to attach the sensor to a robot, and when you drive things around, I want you guys to write down the number of all the sensors and get the resolution of each sensor. How do you trust the sensor, distance sensor, right? And that will be one of the homework, right? So basically, in your engineer notebook, you guys should write down what's the resolution of each sensor. For example, ultrasonic sensor, it can detect up to 5 meters, and you can tell the difference between like 1 centimeter or 2 centimeters, but you cannot tell the difference between half centimeter, right? Something like that. Okay. So once you have this chart in your mind, when you design your autonomous, you know how to choose. You know how to choose your sensor, right? Right. So let's skip all the stuff. So okay. Another thing is color sensor. So color sensor basically detect lights in 3 colors: red, green, and blue. We call RGB. Okay. So this is how people. Last year, people for those teams they don't use camera, they put a color sensor there, right? So if it is yellow, like the cube, it will return high value in both the red and the green because the mix of the red and green is yellow. Right? Right? If it is all white, you will see pretty even number in the red, green, and blue. So this is how they tell the difference between the yellow and the white. Right? Okay. And this is color sensor. And some company is really smart. They merge color sensor to distance sensor, right? With color sensor is shining a line out, detect the beam back, right? So you can basically merge color sensor with a distance sensor, right? Right. So let's skip that. And one thing it is that we have an image sensor. Basically, it's a camera. In this homework, we just let you guys know there's such a thing, right? There will be in a couple of lectures later. Okay? Basically, it's a Vuforia. Use Vuforia. The Vuforia package basically is a machine learning package. What it can does it can recognize target images. How do you recognize target images? You basically have to take one image and put in a machine learning algorithm in Vuforia. It will know where, you will remember, oh, this is the image I know. Now, for example, last year there's a mountain, there's a range, something like that, right? And the target, since it knows the size of the target image, right? If the image is smaller on the camera, then it knows your robot is far away from the target, right? Question?
Did anybody ever use, like, I'm assuming that the image sensor stuff they would have used with the target pictures on the field walls. Did anyone use those?
Last year, no, they don't have to.
Yeah, that's true.
Yeah.
But the year before that, wasn't there some sort of pattern or something? Was that like color sensor?
That was before.
Yeah, that's what for. Okay,
Oh.
so basically, when you see one image is tilted, then the rectangle of the image will turn into be what's Right? Right? Yeah.
No, because.
What?
Yeah. Say if it is rectangle, if the image is correct, perfectly aligned with you, you see a rectangle. Right? If the image is tilted, what do you see?
You still see a rectangle.
Yeah, a smaller rectangle, because you're still level.
Oh, like
Because you're
this.
still level.
Oh, if you're looking at it in perspective, then yeah, trapezoid.
Oh, it is a trapezoid because one side's longer.
Yeah.
Right?
Yeah.
Yeah.
Bottom base is closer to you.
Yeah. Basically, for the camera sensor, if you use with Fourier package, if you do a lot of like a matrix operation and figure out based on the size of the image shows on the camera and the shape of the image shows on camera and orientation of the image on camera, it will give you your position, your relative position of the robot to the image and the orientations. Right? It knows your robot tilt like this way. Know your robot looks like this way. Okay? Got it? Okay. So this is very useful feature. Basically, in last season, you are well supposed to do it is we are guys. If we say do like a fundraising, like a 5K run, right? We can design a robot and stitch a target image on somebody's back, and you just run on the front. The robot will follow you, always follow you.
What's the point of that?
So you just show off.
Oh.
And you can practice your programming skills.
Does it change
And you
depending
can
on
do
how
your
fast you run?
exercise.
So
Does it change
Okay,
depending
who
on
here
how
wants
fast
to
you
run
run?
a
okay, this is basically
Oh my gosh.
remember.
Yes.
Everyone still remember the PID control, right? You can do the feedback control to this. If the further away from, if the image is further away from you, you can move faster. When this thing is, for example, you set up your program such that the robot will stop at about 3 feet away from the image, right?
Imagine
When
you
the-
forgot to put it like
Question?
a stop function for that.
But at the beginning of a 5K, everyone is crowded. So what if someone just like steps on it?
So you can make a long flag, right? Put a long flag with a big flag,
If someone
say
intentionally
Apollo,
steps on it.
so nobody will hit it, right? So basically, with PID control, the robot can do it. If it's far away, it will chase you. If you're too close, you get move back to stay away from you,
Let's make Drake run the
right? So,
Imagine you run
That's
5K
true.
and then it doesn't stop.
so I will put this in as a bonus project. You guys have to do it, okay?
5K.
You have to do it.
Why we
We
want to
have,
do 5K run? Because
have,
the 5K run is the best, like a testing environment to test our driving chain.
We actually have to do
We have
5K.
1.5 months left.
It's just
Oh.
pretty expensive.
Well, we have
It's
1.5 months
just
left.
sensors are very big difference than the other
The
things.
software thing is not only.
No, this is basically it's a software. This is a software. Before there is a
But we
software.
probably won't have
We're gonna
program
spend
an
time
entire
on
5K
during the
thing.
season.
Yeah, that's not
The
realistic.
Android phone is powerful enough to do it.
Oh, so when we're running late to the qualifier, we just put it on the phone when we run. Oh, because we're always like behind.
Kill your brother's middle line.
Okay, that's the last sensor in today's class. It's called optical object detection sensor. Like last year, we have a TensorFlow, right? It knows whether it's a cube or it's a ball, right? We can also do the same thing in the 5K run. We can train the robot to know, say for example, our Apollo tattoo or something strange like a
Tattoo?
something
I want the car 131.
Something.
200 forehead.
or Apollo flag or something, right? Then the robot basically just follow, chase you, right? So there's a lot of things we can make the robot looks really, really cool. Oh, the other thing I forgot to mention is with the gyroscope thing, we can basically impress people by ask our robot to stand with 2 wheels.
Oh god.
Wait, I'll think our current robot can.
Turn
The
it.
robot we're gonna make. Cause like if you stand on two
Dude,
wheels.
if that
On the back
falls,
plate, on the
Yeah, yeah, it's just gonna stay there. Like,
Why?
You want us to make a segue?
if it falls, yeah, you want us to make a segue? Or confusion.
Yeah, technically, we can make a robot such that it doesn't matter it's front, it's top or bottom. Whatever we
Just a
do,
hamster ball of touch
It's a
sensors.
Minotaur from Battle Plus.
right?
Make it only one wheel.
Excuse
One
me.
wheel.
Yeah, it's just a wheel.
It's the
You
tennis
just
racket
cycle.
where we saw.
No, the wheels around the two expansion pumps.
Yeah.
But one wheel is still possible because we can spin a huge like a spinner.
Battle
Use
box.
one wheel.
Battle bots intensify.
I know, right? Legit.
No, just encase it and
And
like
dinner.
just put it inside like a gyroscope thing, and then just have the outside rotate like a ball.
That's a severe.
Okay,
Just
guys. Let's look at homework. Okay, let's look at homework. Okay, the first homework. Modify your robot dance program to use linear optimal. Demonstrate that your robot still can dance.
Wait, coach, I thought you said you were leaving at 7 or.
That's if we weren't doing.
That was the scam dude.
Okay.
That's a scam.
Alright.
Hurry up.
Yeah.
So the reason I want to do this homework it is because most likely in the Atari optimal, we need to use linear mode for fast response, right? Right. So you guys need to program this mode. Second homework it is press button A, your robot move forward. If the robot is blocked by obstacles, touch sensor will be activated and robot should stop. And the robot should keep moving backwards until the touch sensor is deactivated. Right? How many states there? How many states there for state machine?
One, wait for button
Three.
A.
3.
How many three?
4.
4?
I can't see.
Hey, let's count, okay? Initial state is wait for button A.
Wait, button A.
Oh, 5.
Okay, let's do it, okay? Let's count. Wait for button A, move forward,
Detect is blocked by
and detect touch sensor.
And
move
also-
forward.
That's all in one state, right?
Yeah,
Move
one
forward
state,
and
right?
check, and then move backward.
Yeah.
And then
Then-
stop, and then if it fails,
And
stop.
if backwards, they basically move backwards until
It's just being deactivated. It's
you have
not-
4 state, not in state.
No,
You look back, right?
I didn't say look back.
Well, you should look back.
I didn't say it.
Well, I mean, you should.
Then you fail.
I said homework.
Yeah.
You have to do it, whatever it says. If you look back, you
It should
fail.
be repeatable.
No, homework is a homework.
You never said I couldn't look back.
Is there autonomous?
There's no D, okay? Basically, you should basically, alright?
No, C just goes back to A.
The next homework it is you use 3 touch sensors. It's the same thing. Press button A, robot move forward. If front touch sensor deactivated, robot should move back by some steps. Then if left button is activated, robot should turn right. Right activated, should turn left. Right? And if you can demonstrate that, it's good enough. But if you can go extra mile to make the robot can navigate through something, that's a bonus point. Right? I will add that.
1 bonus point?
Let-
Isn't the whole thing worth like 60 points?
Okay. So this one just use compass. Right?
Oh boy.
How many assignments are there?
4.
And
7.
this one is
Sorry.
use the distance sensor.
100.
Have you been counting?
Okay. This one it is write a program use a color sensor.
The IMU
Oh,
the
wait,
whole
that's-
season.
Okay.
I was going to say I was disappointed.
You got
Nice.
0%. What?
5 out of 6. Wait, what?
Hold up.
Wait, what?
Hold on. Wait, what?
Hold on, we do that right now.
Oh my god.
Easy points.
He just got 25 out of 40 points.
Hold on.
Wait, I'm confused.
Hey, let's go! 25
Easy 25 points.
Alright, I will fix it, okay? Basically, I will grade this thing, okay? So what you guys can, I will based on the behavior of the robot.
Does that mean 62% is the minimum we can get?
It won't be that easy, right? So basically, there are totally there's a 40, there are 40 points there. There's a lot of homework. I'm not expecting you to do all of them. There's so many of them, right? So I said like it's about 50% pass rate. That means you just need to do half of it. Half of it. Just pick 1 or 2. Okay? Then you will pass. You don't need to do all of them. You pick whatever the one you think is interesting. Right? Got it? All right. So that's the today's class, right? So okay, let me stop the recording first.